turn the time over to Jamie.
Thanks, Kip. Hopefully everybody can hear me online. Title of my talk today is a multi-scale view of the Yellowstone volcanic system. I'm going to take you through a range of research projects that we've done on Yellowstone and some other stuff that other people have done. And we're going to look at the Yellowstone volcanic system basically from its deep roots in the mantle up to the very shallow hydrothermal system on the surface. I have a lot of organizations that I like to recognize here. I'm with the University of Utah Seismograph Stations. We are part of the Yellowstone Volcano Observatory. We're a member organization of that. And our part in that is to monitor Yellowstone for earthquakes and put out timely information on earthquakes as they happen, locations, magnitudes, other related stuff. And we communicate that information to USGS, the Park Service, other interested organizations. We are partially funded by the USGS for our network in Yellowstone through a co-op agreement. A lot of the research topics that I'll show today are NSF funded. Of course, we work closely with the National Park Service on both science stuff, operational stuff, and also they provide the permits for most all the stuff that we do in the park. And I also want to recognize the Brinson Foundation, who provides some funding for me and the work that I do. Of course, there's a lot of people that I should list that are collaborators on this project. I only listed a few here, but there's way more that wouldn't fit on a computer screen. But main people are at the University of Utah, Fanchi Lin, Keith Coper, and Bob Smith, who I've worked with on a lot of these projects that I'm going to show here. At the Park Service, Jeff Hungerford, who's the park geologist, and Andy Carlson, who does all the permitting for the work that we do in the park. Shinmei Wu, who used to be a PhD student here and a postdoc. She is now moved on as a postdoc at ETH in Zurich. Guaning Pang, who was also a PhD student here, who finished recently and is now a postdoc at Cornell. And then Xinhua Huang, who was a postdoc here with Fanchi and is now at Academia Sinica in Taiwan. And of course, there's way more people that they would take too long to talk about, to put in here. So I just want to start out by giving a kind of a brief tectonic overview of Yellowstone, and then show some features on a map that you're going to see in other maps throughout the talk. So if I can get my mouse working here. So this is the Yellowstone National Park outline right here, shown in this black polygon here. Within Yellowstone, you'll see a number of faults. You can see these smaller faults here and the thin black lines, and then the thicker lines in red are kind of the more major faults. All of these are basin and range type normal faults with extension rates, mostly in the east-west direction, except for the Hebgen Lake fault here, which is and the Centennial fault, which is rotated to more north-south direction. We have two resurgent domes in Yellowstone. We have the Mallard Lake Resurgent Dome, shown by this dashed line, and we have the Sour Creek Resurgent Dome, shown by this dashed line, and then three major caldera boundaries in the Yellowstone region. Caldera 1, which is the largest, is this outline shown here, and that occurred 2.1 million years ago. Some people think the boundary actually goes up more to the north up here. Caldera 2 is a smaller caldera, the Henry's Fork caldera, which is down here in Idaho, and that was 1.3 million years ago. And then Caldera 3, which we call the Yellowstone caldera, and produced a lava creek tuff, is this outline here, which is wholly contained within the park boundary. And on most maps, you'll see in the rest of this talk, you'll see this Caldera 3 and these two resurgent domes as a reference. This is the network that we operate. In Yellowstone, we at the UUSS operate 30 seismometers, seismograph stations up in Yellowstone. And then there is 15 or so other instruments in the area that are operated by other institutions that we record as part of our monitoring effort. These are color coded by the type. The red and orange are broadband, and blue are broadband sensors. Anything that's yellow is a short period sensor. Some of them have 3 components, some of them only have a single vertical component. Some of the stations that we record that are not ours are these B numbers, B208, B944. These are borehole seismometers that are operated by UNAVCO. They were installed as part of the Plate Boundary Observatory, as part of the EarthScope project. This station here is operated by the state of Montana. And then we have some USGS stations down here, part of the Teton network, and one USGS station here at Lake. The rest of these are our stations that we maintain and operate. Here's a seismicity map of Yellowstone. This is from 1972 to 2021. There's roughly 55,500 earthquakes on this map that have been located. The majority of the seismicity in Yellowstone is located in this east-west band seismicity right here, from the Hebgen Lake area over to the Norris Geyser Basin. We have these kind of an echelon northwest, southeast trending zones of seismicity that come down through the caldera. These earthquakes in this area in the caldera tend to be much shallower than the earthquakes up in this area and even down here to the south. You can see the magnitude breakdown here. In this time period from 1972 to 2021, we've had 1 magnitude 6, which is this event right here, 1975, magnitude 6.1. They call it the Norris earthquake. 2 magnitude 5s, 29 magnitude 4s, 404 magnitude 3s, and then most of our seismicity, in fact, greater than 99% of the earthquakes that occur in Yellowstone are magnitude 2 and smaller. Now, if you look here, the circles in blue here are events that we've categorized as swarm earthquakes or part of swarm sequences. So swarms are just kind of clusters of seismicity in both time and space, and they're really common in volcanic areas, Yellowstone included. And as it turns out, about half of our seismicity in Yellowstone occurs as part of earthquake swarms. And some of the larger ones that will show, the largest swarm in Yellowstone is not shown in here because the swarm seismicity is only from like 1995 to 2021. But this cluster in here, this is the 1985 swarm. This is the largest swarm we've ever recorded in Yellowstone. This is the 2008 Yellowstone Lake swarm. Right below it is a swarm that occurred just earlier this year in Yellowstone Lake. This is the 2010 Madison Plateau swarm, and then I'll show you a little bit on this swarm. This is the 2017, 2018 Maple Creek swarm. This is the second largest swarm we've ever recorded in Yellowstone. Another way to look at it, this is seismicity through time, also showing deformation on here as a comparison. So each one of these bars is a 3-month time period. And you have time on the x-axis and number of earthquakes per quarter on the y-axis. And you can see through time the number of earthquakes that we've located. Each one of these big kind of spikes is a swarm that's occurred in the Yellowstone region. Here's the 85 swarm here. The 2017 swarm of these 3 spikes right here. That's labeled here. Here's the 2010 swarm. Right here, and then this is the swarm in Yellowstone Lake that occurred just earlier this year. These 2 lines, the black line and the green line, these are vertical deformation, and you can see the black is deformation in the caldera, and green is deformation just outside the caldera in the Norris area. And these lines are taken from various data sources. Earlier, they're taken from leveling lines that were done throughout Yellowstone. Then we started campaign GPS surveys, and then we have more permanent GPS sites. Anything from about probably 2000 on or 95 on is probably mostly from permanent GPS sites that have been operating in Yellowstone. And then this is in the Norris area, and a lot of times these two areas in Yellowstone are anti-correlated. So when the caldera is subsiding, Norris is going up, and vice versa. And you can see here during this time period, the caldera overall was going down and Norris was going up, and then the caldera switched to uplift and Norris went into subsidence, switched around here, and then we had this accelerated uplift here at Norris, which culminated in a magnitude 4.8 earthquake in the region, and then abruptly turned around right after that earthquake. And then it's been kind of flat ever since at Norris, and the caldera has continued to subside to this day. But one thing to look at is a lot of times when you have these really big swarms, they come during times of caldera reversal. So here you change from uplift to subsidence, and we had the big 85 swarm. 2010 swarm, we've had accelerated uplift, switch to subsidence. So there is some relationship between when these swarms are occurring, where these swarms are occurring, and how the deformation in the caldera responds to these swarms. Just for an example, this is the 2017-2018 Maple Creek swarm. On the left here is a map view of the locations that come out of the catalog that we produce at UUSS. To the right is a paper by Pang et al. And using some kind of advanced location techniques, double difference locations, getting much better relative locations than what we have in the catalog. And you can start to see these different kind of distinct structures that are rupturing during the swarm. And if you look at cross sections, for example, A to A prime shown here, you can see these different structures that are rupturing at different parts of the swarm. So we can, we've done this for a bunch of the different swarms. We have research projects going on right now looking at swarms. So it's a pretty hot topic, looking at earthquake swarms, and not just at Yellowstone, a lot of different places in the world. But you can learn a lot more about the process of these swarms and whether they are accompanying water transport, CO2 transport, or even magma moving around in the crust. You can look at those types of things and then see if they're happening. For example, this swarm, when it was first occurring, people were wondering if it was occurring. This is the kind of the eastern extent of the Hebgen Lake Fault. And this is the fault that ruptured in 1959, magnitude 7.3, just outside of Yellowstone. People were wondering if this swarm was occurring on that fault. And as it turns out, looking at these, we can pretty definitively say that it's not occurring on that fault. So those are the type of things that you can learn more about by looking at these higher resolution locations. Okay, so I'm going to start taking you through some imaging projects that we've done. This is not our group, this is another group, but this is looking at teleseismic tomography using earthquakes from around the world. You can see here, this is Yellowstone right here. These are the earthquakes that were used during this project. And they're using these earthquakes. Here's the source, here's the rays traveling deep within the earth and then coming back up and being recorded on the network, which are these triangles all around Yellowstone. And that's the data. And then we invert this for velocity, seismic velocity. And we're going to look at this cross section here from down here, this black circle up through this orange circle here. And that's the cross section I'm going to show next. And this is a snapshot of the velocity structure of the mantle. And you can see here, red are lower seismic velocities. And you can see you have this kind of persistent feature that's more or less continuous from the lower mantle all the way up to beneath Yellowstone. And in this paper, they interpret this as the Yellowstone mantle plume. And this is what's bringing heat and energy up from deep within the earth up to beneath Yellowstone. So that's kind of the deep roots of the Yellowstone volcanic system. And now we're going to start looking at much shallower in the crust. And we can go through kind of a history of what we've done here. Starting with in 1982, this is Shilley et al. 1982. This was from an array that was put out in Yellowstone, and then a bunch of explosives were set off in various places in and around Yellowstone, which there's no way you could do that now. And you can see this is like a fan diagram. On the x-axis is azimuth, and on the y-axis is time. And you can see here going from 180 so south and rotating through this diagram, you can see within this area, which are these two dotted lines here, these signals here are delayed. They're coming in later than the stuff before it and after it. So this is kind of the first image that there is something beneath Yellowstone that's slowing down this energy as it travels through Yellowstone. And then this is using the same data set and Lehman et al. 1982. And here you can see this is a cross section from the southwest through the northeast, through that long axis of the Yellowstone caldera. On top are seismic velocities. On bottom are densities. And you can see they have lower velocities underneath the caldera and higher velocities on either side of the caldera. And then you fast forward to 1984, Benz and Smith, using 422 travel time observations. They inverted for P wave velocity, and you can see here in their contours, they have two kind of main areas of low P wave velocity, one on the southwest part of the caldera, which you can see again on this outline here, and one on the northeast caldera. If we move forward in time, Miller and Smith, 1999. Now this is using 7,942 earthquakes in the Yellowstone region, over 66,000 travel time observations. And then they also use those same controlled source explosions as part of this inversion. And this is their P wave velocity model. This is again a cross section from southwest to northeast. And again, you can see they see these low P wave velocities underneath the caldera, which they are interpreting as areas of partial melt. And they see this strong low VP velocity area up here to the northeast, which they are interpreting as a saturated and overpressured fracture zone. And then Houston et al. 2004, this is using 3,374 local earthquakes. And this is the first time that S waves have come into the picture here for Yellowstone. Everything before that were all P waves. And here we've introduced some S minus P times. And here they inverted for VP, which is P wave velocity, and the VP-VS ratio here. But they only had resolution for VP-VS in this area, which is where that east-west band of seismicity where most of the earthquakes occur. So that really comes into play in interpreting this low velocity here. Again, this is the main body of the magma reservoir. And then this area of low velocity here, which is very prominent due to VPVS and the P wave velocities they see, they interpreted this as a CO2 rich gas filled body up here on that caldera border boundary. And then this is the stuff that I did for my dissertation here at the University of Utah. Again, I used 4,520 events during this 26-year time period, 48,622 travel time observations. And you can see on this map here, the gray lines kind of represent the ray paths going from source to each receiver. And it kind of gives you a good representation of where you have resolution, where you have coverage, where you're sampling the Earth. So you can see again, up here where we have a lot of stations and a lot of earthquakes, we have very good coverage here. Down here in the caldera, where we have fewer earthquakes and they're much shallower, we don't have as good a coverage here, but we still have fairly good coverage covering the entirety of the caldera. Of course, when you get outside where you have no earthquakes and no stations, you have no ability to resolve that velocity model. And here's my model. On the top are 4 depth slices, one at 2 kilometers, 5 kilometers, 8 kilometers, and 14 kilometers. And again, here you can see that very shallow low velocity zone on the northeast of the caldera that was seen previously. And you can see that shallow velocity body that Houston et al. Interpreted as a gas-filled body here. When you get down to 5 kilometers and 8 kilometers, you're seeing kind of the main body of the Yellowstone magma reservoir. And then down about below 14 kilometers, we see the bottom of it. And then below 15 kilometers, we lose resolution. So if you look at cross section here from X to X prime, which is shown down here, again, you can see the main body of the Yellowstone magma reservoir here. And then you have this shallow area of low velocities up here to the northeast, and these are connected. We did a lot of resolution tests to see if this was just an artifact of the inversion, and see if we could resolve this. And we do believe that these are connected by low velocities. And we interpreted this as an area of a body of partial melt. Given the velocities we're seeing, we estimated anywhere from 5 to 15% partial melt in this main body of the caldera. And then we interpreted this shallow area as an area of hydrothermal fluids and gas-filled fractures. Up here, the star is the location of Hot Springs Basin, which is one of a very large and active hydrothermal system sitting right on top of this feature. And this was kind of our schematic. So we had the mantle plume coming up, and then we have this shallow crustal magma body sitting beneath the caldera. We didn't know what was happening in between there because we don't have resolution in between there. So we were just guessing basically what's happening here. So that kind of spurred on the next project, and that was published in Huang et al. 2015. And here we did a joint inversion using the same earthquakes that I just showed you in the model before, but we added in 329 teleseismic earthquakes from Schmatt and Lin 2014. And then we jointly invert for using both of those data sets, and that helps us get that resolution and kind of that lower crustal depth. If you look at the model here, these are some other depth slices again. So this is 2 kilometers. Again, you're seeing similar stuff to what I showed previously. You have that northeast low velocity and that low velocity here in the northwest caldera boundary. 8 kilometers, you have the main body of the upper crustal magma reservoir. At 14 kilometers, you're seeing the very bottom of that. And then starting at about 20 kilometers, you start seeing an additional low velocity body sitting beneath the caldera. And then at 70 kilometers, that's gone, and you're starting to see the mantle plume sitting here. And again, you can see that here shown by the arrows. And if you do a cross section, A to A prime is this one on the long axis of the caldera. Here's that upper crustal magma body. Here's that lower crustal magma body. And then on these ones, B to B prime and C to C prime, which are going across the caldera this direction, you can start seeing the plume down here. So then we can update our schematic here. You have, again, the plume coming up. We now know that there's a lower crustal basaltic partial melt body. And then we have this upper crustal that we've seen before. That's interpreted to be rhyolitic partial melt. This is what's providing all the material for the explosive Yellowstone eruptions in the past. Okay, so some questions still arise though. We don't know how each of these bodies are connected. We don't have the resolution yet to see those small features. And then also a big question, what's happening above this magma reservoir? We know that there's a very active hydrothermal system in Yellowstone sitting above this. So, what's going on with that? How does the upper crustal magma reservoir interact with the hydrothermal system sitting on top of it. So that was kind of the impetus of one of the questions we want to answer with this project. This is an NSF funded project between myself here with collaboration with Fanchi on his NSF funded career grant, and then with Brandon Schmatt at the University of New Mexico. We installed around 650 3-component geophones throughout Yellowstone in 2020. We might have been one of the only ones to do a large scale project in 2020 in Yellowstone, or in a lot of places in the US, but we were able to get it done. We installed them mostly along the road system in Yellowstone, except for this, along this trail connecting the 2 roads here. We had 2 really dense parts of the array here across the caldera on this road, and then across the caldera here on this road. And then as part of this, we brought in a Vibroseis truck, which you can see here. And along these dense lines, the Vibroseis truck would drive, and each pull out, it would stop and shake the ground. And then we would record that energy as it propagated through the array. And we did all this in the middle of the night, so it'd be quieter and there wouldn't be as much traffic in the park. And this is a Vibroseis truck. This is it's only producing P waves, so it's only producing vertical forces on the ground. And one of the goals of this project is to use those P waves as they dive down, as they convert to S waves at the top of the magma reservoir and then come back up. We want to use those S waves as they come back up and see if we can get an idea of how delayed those shear waves are as they travel through that upper portion of the magma reservoir. And that way we can get a better idea of actually how much melt is in that upper part of the magma reservoir. So that's one of the goals of this project as well. And I'll show you some early results of the bigger picture of this, doing some ambient noise tomography on the array as a whole. But first, I'm going to show you a video of the Vibroseis truck in action, and we did these at each spot. It would stop and it would shake for 20 seconds. It would go through a sweep of frequencies, and then we would do that 20 times at each stop, and then we can stack those to get better signal to noise ratio. And this is the video of a truck. And what I did is I put my phone on the ground as it's operating, and you'll be able to see it kind of vibrating at different frequencies as it goes through. And I put this black line so it's easier to see the vibration. Hopefully this isn't too loud, but you'll see that there's the hydraulics starting to go. So it's shaking the ground now, and you'll start to see the vibration as it goes. So now you can kind of see it starting to shake here at a kind of a higher frequency. Let's see, here it goes. Now you can start seeing the shaking, but the higher frequencies, then it'll sweep through and you'll see it kind of switch to lower frequencies as it goes on. Now it's getting a little bit lower frequency. So like I said, we would do this 20 times at each site. And we would give, I think, maybe 10 or 20 seconds in between each shake, and then do it again, and then move on to the next site. That data is being worked on at the University of New Mexico right now, and hopefully they'll be giving us that data pretty soon. Now, looking at the ambient noise, this is work that Xinmei Wu was doing as part of her postdoc here at the University of Utah, and she's kind of continuing finishing it up as she's moved on to ETH. But you can see the cross correlations here. This is cross correlations using this permanent station here to the northeast, station YNE, and they're cross correlating that station with all other stations in the array. And here you can see on the positive time lag here, you can see the signal starting here at YNE and then working its way through the array. And the slope of this would be the velocity that Rayleigh wave is passing through the system. And you can see here, this is like kind of a time snap of that energy, the high amplitude energy moving through the array right here. if we showed this movie, it would start here and it would radiate out through the array. So, we can see that we have good signal moving through the array that we can use for imaging. And just to show you a comparison of what the dense array can do for us, this is doing looking at velocities just based on the permanent array and other arrays that were installed in the past around Yellowstone. And you do see low velocities here, but you can see that it extends up to the north outside the caldera. And if you compare that to doing the same thing, only using the dense array, you can see not only do you see more kind of what you expect, low velocities taking up pretty much the entire caldera, but you also see much lower velocities here. Look at that. This is just for an 8-second phase velocity, Rayleigh wave phase velocity. So one snapshot, but you can see how the dense array kind of really helps in the inversion here. Now, we use both Rayleigh waves and love waves kind of for two reasons. One, these are the sensitivity kernels for Rayleigh waves and love waves. And you can see here at different periods, they're sensitive to different depths. And for example, here at 8 seconds, you're most sensitive to about 10 kilometers, but the love waves are sensitive to much shallower. So using both of them, you can use the love waves to resolve the shallower velocity structure, and you can use the Rayleigh waves to help with the deeper structure. But also another reason why you want to use both of them is you can look at anisotropy as well, because the way these surface waves propagate, love waves are moving in this direction, but they're oscillating in perpendicular to the direction of travel. So they're oscillating horizontally here, as opposed to Rayleigh waves, which are retrograde. They're oscillating mostly vertical as it propagates to the right. So you can use the love waves to get what we call VSH, or the horizontal shear wave velocity, and you can use the Rayleigh waves to get VSV, or the vertical shear wave velocity, and you can use both of those to get anisotropy. And this is a paper that was published prior to in Zhang et al. 2018, and they saw positive anisotropy in the caldera, which means that most of the features here are horizontally orientated. So this is probably stacks of sills in the magma reservoir, as opposed to dikes. It's dominated by sills here in this upper crustal magma reservoir. And we can do the same thing, but first we can look at the isotropic. Before we get into that, we can look at the isotropic solution, where you're just assuming an isotropic medium where it just travels at the same in all directions. And you can see here's the depth slices again, 1 kilometer up to 10 kilometers. And you can see the low velocities on the northwest caldera boundary in the shallow portion. And then you can start seeing the main caldera, the main magma reservoir here underneath the caldera, down to about 10 kilometers. And the reason why this is good, in a sense, better than what we showed before, is that this is shear wave velocity. So shear waves are much more sensitive to fluids in the crust. So this can really give us a lot more information than we had before, which was only P wave velocities. If you do the looking at anisotropy, here's the VSV. So we've only solved for the VSV here, and you can see similar patterns here. You can see the main magma body here underneath the caldera, and you can see this structure to the northwest. And then looking at VSH, much stronger lower velocities here on the northwest part of the caldera. And again, here's the main body of the caldera. But if you use these to look at anisotropy, you can get stuff like this. And again, this is all done by Xin-Mei Wu, who's hopefully just finishing this up, and we'll be writing this up here pretty soon. But again, we do see positive anisotropy in the main body of the caldera. So again, that would support kind of a sill complex. But we do see negative anisotropy up here in this area that was previously interpreted as a CO2 body. So this would show us, this would, could interpret this as more kind of dikes, more vertical features feeding this low velocity body up here. So that's something neat that we can look at that we didn't have before. Okay, so now the hydrothermal system sitting above the magma reservoir. This is an array we put in 2016 in the upper geyser basin. So Old Faithful Geyser is sitting on the star. We're going to focus on this array right here, and we use the signals from this array to look at kind of what the velocity structure is beneath the upper geyser basin. And with these arrays, you can make kind of cool videos like this. This is using cross correlation. This is the source station. And you can see the signal as it propagates out from this station through this array. The colors are going to be the vertical, representing the vertical motion. And then the lines that you'll see rotating will be the horizontal motion. You can see here, here's the signal, and here's it rotating through that array. So there's kind of two things here. One, you can see that these signals here are, one, amplified in this area as opposed to other places, and they also kind of linger. They just kind of bounces back and forth. It gets trapped in this area, so that, you know, we can get some information about hazards and that kind of stuff by looking at stuff like this. But if you look at the signal from Old Faithful itself, we found this, you know, in particular, this 1 to 5 hertz signal. And you can see, again, we're looking at this array. Here's Old Faithful. This is 50 minutes before an Old Faithful eruption. And then the colors are the incident angle of the signal, and then the lines of the direction that it's pointing to. So you can see here, it's all pointing kind of close to this area right in here. And as the movie goes on, you'll see it change. Here you go. It's pretty shallow here. And then here's the eruption. It kind of changed and got a little bit deeper in this area, and it's slowly getting back up to shallow as the colors turn more blue. And you can kind of see it switch. So you're seeing that signal. It's very shallow before the eruption. As the eruption occurs, it dives down and slowly works its way back up towards the surface. And you can see that in cross section here. Again, here's the signal. It's shallow. Here comes the eruption right now. It goes deeper, and it slowly makes its way back up. And we can use this to kind of infer the plumbing system of Old Faithful Geyser. And we do that. Here's our schematic. So you can see that signal. Most of the time, it sits right in this area, about 20 to 25 meters depth. And then it dives down to about 80 meters down here, and slowly works its way back up to this area prior to an eruption. And you can see this break in the slope of the velocity that's moving up. And that occurs right kind of at this geologic boundary from a drill rig nearby, where it goes from rhyolite flows up into glacial sands and gravels. So we interpret that as a change in the diameter of the pipe. So that changes the velocity of where this interface, and the interface we're seeing is where we're seeing boiling in the water column as it slowly works its way up prior to an eruption. We can do the same thing for different geysers. This is Steamboat Geyser. This is the tallest active geyser in the world. When it erupts to 300 feet in that range. This is all the eruptions that have been recorded since the 60s. There's been 3 major periods. The one in the 60s, a major period in the 80s, and then this current active period that we're in right now. You can see there are 85 eruptions in the 60s, 39 eruptions in the mid 80s, and then so far in this current sequence, we've had 144. Actually, there's 145. There's one eruption that just occurred that happened after I made this figure. But very few of the eruptions occur outside of these active periods, and in fact, only about 6% occur when it's not in one of these active phases. So we took advantage of this active phase. Here's just focusing on this active phase. This is a deployment that we put in that we caught 4 eruptions in 2018. Another deployment we did around Steamboat in 2019 where we caught 7 eruptions, and then one we did earlier this year, and we only caught 1 eruption during this kind of slow period. And I'm going to show you just some data from that. This is a picture I took from a helicopter. Steamboat is right here. This is the parking lot for Norris Geyser Basin. The museum where we have our permanent station is sitting right here. It's about 300 meters from Steamboat. Cistern Pool, which is just down the hill from Steamboat. We know that these two are connected somehow underground, because every time Steamboat has a major eruption, Cistern drains completely and then slowly fills up. And then it happens all over again. So in fact, when I took this picture, you can see that it's mostly drained here. This was shortly after an eruption. But again, one thing you can see here is just the scope of these eruptions. You can see the trees here are completely covered in silica from these eruptions as the dominant wind direction blows it this way into the parking lot, actually. And you can see this is my car after one eruption. And I had to replace the windshield because the silica comes down and just bonds to the glass on your windshield and you can't get it off. So I just replaced the windshield after that. And a lot of cars, like you'll see cars just completely wrapped. They wrap them so they don't get slimed by Steamboat. People park out on the road. But this is the array we put out in 2018, mainly just around Steamboat. We had a couple stations around Cistern. In 2019, we came back with a larger array with more stations down by Cistern down here. I'm going to show you some results from this deployment. A lot of the stuff I'll show you is from this station, 1028 right by Steamboat and 1030 right by Cistern. These are what the stations look like. This is me putting them in right next to Steamboat. These little geophones here, these are 3-component seismometers that go in. They last for about a month. This is an eruption. This is recorded. This one on the top is recorded from our permanent station. This is from station 1028 right next to the vent. You can see the difference in amplitude here. This is times 10 to the -5 here on the units here, and this is 0.02. So this is much higher amplitude here than we're seeing at the permanent station, which is about, again, like I said, 300 meters away from Steamboat. So we can get much more information with these geophones sitting right next to the eruption. Again, this is about 2 hours of data. And this is again a picture of Cistern. This is right after an eruption. So the eruption was on May 4th at 23:15. This is the next day at 10:28 a.m. So it started to go down. This is 2 days later. And now it's actually coming back up now. It has completely drained, and now the water is coming back up. So you can see kind of what happens with Cistern after Steamboat erupts. In this deployment, we actually put a temperature sensor and a pressure sensor in Cistern. And you can see the relationship between temperature and depth of the pool is in relation to the seismic signal. This is that 1 to 5 hertz signal right here shown in the spectrogram. So this is period on the y-axis and then time. And this is the signal of interest right here. You can see here's the eruption right here, this dotted line. And then immediately the temperature starts going down in Cistern. But the water level, it continues to boil for about an hour, and then the water level doesn't start dropping for about an hour. And then it starts dropping. And here, the water level dropped below the instrument. So now it's just recording air temperature here. And then again, the water has come up now, starting at this time. So the temperature, jumps up to here. And then you can start boiling starts happening about this point when the 1 to 5 hertz signal returns, and you see this big jump in temperature. Interestingly enough, the temperature stays up above boiling for a while, and then it drops, at least at the level of where this sensor is. But the pool continues to boil, and now it's in overflow. So it's level here. The water depth is level until the next eruption, and it just repeats itself. It's amazing that it's almost a carbon copy of what happens each eruption with Cistern and Steamboat. But again, we can use this 1 to 5 hertz signal to back out the plumbing structure of Steamboat. And this is just all 7 eruptions showing the signal at Steamboat and the signal at Cistern. And it doesn't, the seismic signal doesn't always look exactly the same. There's some slight differences from eruption to eruption. But mostly it does the same thing over and over and over. In this instance, we want to make sure we're using body waves. So we can look at, for example, station A right here. You can see that the radial component and the vertical component are in phase. So that means this is a body wave, a P wave. And then as you get farther, this converts to a surface wave where they're out of phase here. So we want to make sure we use only body waves. So we have to make sure that the incidence angle that the difference here is less than 30 degrees. So then we can know that what we're looking at are body waves and not surface waves. That way, the incidence angle is actually pointing directly back to the direction of propagation. So we can see here, this is for a steamboat source here. You can see 10 hours before the eruption, it's all pointing back here, and it's pretty shallow. 8 hours after the eruption, it's still pointing back in the same area, but it's very deep here. This is a cistern source down here. You can see again, it's pretty shallow, 8 hours or 10 hours prior to the eruption. Interesting enough, with a cistern source, 8 hours after, it's very deep, but the source is down here, south east of cistern. So the plumbing structure of steamboat is pretty much vertical, but cistern dips down to the southeast. And again, the similar stuff that I showed for Old Faithful, we did for steamboat. And again, these are snapshots of time. The source at minus 10 hours is right beneath the two sources, very shallow. After the eruption, the cistern one moves down to the southeast and gets deeper. Steamboat just goes down vertical and gets deeper. Steamboat comes back up faster than cistern does, but eventually they both get back up to right beneath their sources. And we can build an isosurface for these sources, or you can see, here's a movie showing the same thing. You'll see it, there's the eruption. So everything got deeper, then this slowly migrates back to the source. And we can build an isosurface here. These are both the same model with different look angles. This is looking to the northeast. Here's the steamboat plumbing structure down to about 140 meters. Cistern is vertical down to about 65 meters and then dips down to the southeast. And here's a different look angle. One thing is we don't see the connection between the two. We know they're connected somehow. So that means one of two things. Either the connection is aseismic, it's not producing any seismic signals, or it's just deeper than what we can resolve here. So one way to test that, we went in and put in another array this year, earlier this year. We added a bunch more stations down in this area to see if we can look and see if we can see that connection much deeper. We also put more stations throughout the whole basin to see if we can get other velocity for the basin as a whole. Another project we did, this is looking at microseism generation on Yellowstone Lake. So this is a NSF funded project with me and Keith Coper here at the University of Utah in collaboration with Rob Sohn at Woods Hole. And we put out, again, a bunch of seismometers around the lake and on the islands in the lake. We put out weather stations. We put out wave gauges to directly measure the wave period and height. And then during this project, there was another project going on that put in lake bottom seismometers here. So we also use those as part of this project. And you can hear, here's a spectrogram of the wave gauge. So this is period again on the y-axis and time for the whole thing. And you can see daily generation of these waves as they get built every single day as the wind picks up on Yellowstone Lake. Anywhere from about 1 to 4 second periods for these waves. And then this is the spectrogram for the lake bottom seismometer. And you can see again, you can see the microseismic signal being picked up every day as the microseismic gets built. Here is the dominant wind directions from all 4 weather stations, and it's dominantly coming out of the southwest as it blows across the lake each day. Here's one of the nodal seismometers. This is one on Stevenson Island, and you can see again, you can see the generated microseism here. We see a lot of surface noise here on these nodal stations as well at higher frequencies. But this is the microseism coming through here. This is a station on the east shore of Yellowstone Lake. And again, you can see the microseism being generated here. This right here, up here, this is the ocean microseism that's being recorded. on the nodals as well. So this is the lake microseism. This is the ocean microseism. I'm going to show you some close-ups during this week of time right here. These are the wave gauges. So I've outlined the period of the wave. So we're directly measuring the period of the waves on these wave gauges. And if you know about microseism, there's two types of microseism being generated. There's the primary microseism, which is generated by direct interaction of the waves and the lake bottom. And that typically happens in shallower areas of the lake. And the period of the microseism is the same as the period of the waves on that microseism. There's also what's called the double frequency microseism or the secondary microseism. And that's generated by different sets of waves interacting with each other in the water. And that energy propagates through the water column down into the solid earth. And the microseism there is called the double frequency. So it's double the frequency of the waves or half the period of the waves. So what we did here is this is a direct measurement of the wave period or what we would expect the primary microseism to be. So in the next figures I'll show, I'm going to show this outline in black as the primary microseism, what it should be, and we'll take half that period and we'll show that in green as where we would expect the double frequency microseism to be. And you can see here, this is one of the lake bottom seismometers. We're not recording the primary microseism at all. You can see there's really no signal in these black outlines, as you can see here. But the green outlines match the signal almost perfectly. It's amazing. You would think that this is a contour of this signal here, but it's not. This is just half what this signal is here. So it's pretty clear that we're recording the double frequency microseism at the lake bottom seismometer. At station 002 on Stevenson Island, we are recording the double frequency microseism as well, and maybe a hint of the primary microseism here. We're not really sure about that. But if you look at station 013 on the lake on the east shore, we're getting both. We're seeing the primary microseism here and the double frequency microseism here, which is interesting. And if you look at a map here, I've just color coded which stations see. The green are the only 4 stations where we for sure see the primary microseism on the nodals. Anything in yellow, we might see the primary microseism. Anything in red, we for sure don't see the primary microseism. And then black is bad data or not working. So one thing to think about, there might be some, for primary microseism generation, there could be an influence on the bathymetry of the lake bottom or the geometry of the lake shore. We're not sure, but that could play an important role on the generation of the primary microseism. And then what we're doing next, this is an SF funded project with Fan Chi and myself here at the University of Utah, and then Michael Manga at Berkeley. Again, we're going back to Old Faithful, and we're going to redeploy these dense arrays we did before that I showed previously. But we're also going to put an even denser array right around the cone of Old Faithful, which is this black star. This is an array that was put in back in the 90s by Sharon Kadar when he was at Caltech. And we're going to reoccupy the same sites and see if we can see even shallower structure beneath Old Faithful. But also part of this, we're doing mini arrays around 3 pools. I'm just showing doublet pool here. This is doublet pool right here. The red are the seismometers we're going to put around it. And then also at each pool, we're going to put in a hydrophone in the pool, some IR imagery, some video, both above the water and below the water. We'll drop a camera in the pool. We're going to do some pressure transducers, temperature transducers in the pool. We'll do multi-gas on the surface to record these gases coming out of the pool. And then Kip and will help us doing noble gas concentrations and total dissolved gas pressure within the pools as well. So we're going to record all that data at the same time as we're recording seismic data and see if we can see kind of what's happening in these pools. Doublet pool in particular, it's very interesting because every about half hour, it starts thumping. You can feel it and hear it, just thump, thump, thump. And then the surface just bounces up and down. That happens for about 7 or 8 minutes, and then it stops, and then it does it again like a half hour later. So one hypothesis is that it's like an underwater geyser eruption that's not making it to the surface. So we're going to see with the video and the temperature and all these other things, see if we can see how these pools are how they act. And we'll do it at 2 other ones too, and compare. So that's what we have coming up. And that's the end. So I'll leave you with a video of Steamboat Geyser erupting back in